Hi, and welcome to the first of what I assume will be many presentations in our IB physics class. Today we're going to be starting our first topic, which is mechanics, and the first topic inside of that is motion. And so we're going to start with motion just along one dimension, which is the simplest motion, and it'll teach us a bit about how we describe motion and how we think about things as physicists. So let's get moving. The goals for this lesson connect to the essential idea that motion may be described and analyzed in terms of equations and graphs. And in this first presentation, I really want to start getting you comfortable with some of the terminology of kinematics, or the study of motion. And those would be things like displacement, velocity, acceleration, speed, distance traveled. We're also going to look at distinguishing in one dimension vector quantities from scalar quantities, how to distinguish instantaneous values from average values, particularly for velocity. And we're going to look at the mathematical definitions for velocity and acceleration, which are going to be the basis for a lot of the equations that we use for kinematics moving forward. So let's get started. First, I want you to think about moving along a straight line. What are the things that you can do? How would you describe how you could run if you were constrained to run just along a straight track? What would you be able to do? I'll pause for a second. Hopefully some of the words that you came up with to describe your motion appear on this list. I've grouped them, so we have things that describe standing still, moving forward, moving backward. These are all phrases or words that are associated with the velocity, how a person is moving. You might also think about maintaining your speed or speeding up or slowing down or changing direction from moving down the track to moving the other way. And these are all terms that are associated with acceleration or a change in velocity. And in physics, especially in introductory physics, we're going to describe the motion of all objects in terms of the position, where you are, velocity, how your position is changing, and acceleration, how your velocity is changing. So those three words are our key words. When we talk about quantities of motion, it is important to distinguish between vector quantities and scalar quantities. Vector quantities are quantities that have both a magnitude and a direction, and scalar quantities have only a magnitude. Here's some examples from across physics. So for vector quantities, we have things like velocity. You can move 5 kilometers an hour to the north. Force, you can push with 10 newtons down. Field, you can have an electric field strength that points to the east. And displacement, you can move, 10 meters to the right. On the other hand, you have some quantities that only have a magnitude. Things like mass, 10 kilograms, temperature, 270 Kelvin, time, 10 seconds. And in terms of kinematics, there are also two quantities that we think about that in physics we refer to specifically the magnitude. And that's when we talk about the word speed or distance traveled. And those are going to be in contrast to velocity and displacement, which are the vector quantities. One thing that's important is later we'll learn about vectors in more than one dimension, but in one dimension, your direction, either forward, backward, left, or right, is really indicated by just the sign, the positive or negative sign attached to the number or the quantity, the magnitude of the velocity and displacement. So you're looking for positive numbers or negative numbers for forward or backward. Come back to this idea of displacement and distance traveled. Consider motion that takes you from point A to point B. I know that this is in 2 dimensions, but don't worry about that for right now. It's just an easier picture to look at. So you might consider yourself taking a path that follows this purple track here. The distance traveled would be as you measure along that path. So maybe this is a hiking trail and you hike for about a mile. On the other hand, the displacement from start to finish is the straight line distance between the start and the end. This has a specific direction from where you begin to where you end, or on the other hand, the distance traveled is just a magnitude of how far you've covered. If we move into one dimension to look at this a little bit more quantitatively, you can imagine somebody starting and following this yellow path, traveling 70 meters to the right and then 30 meters to the left, or they could travel 40 meters to the right. They would end at the same location here, but the distance traveled and the displacement, the distance traveled in the two cases would be different. On the other hand, the displacement would be the same. Because distance is the traveled length of the path that you follow. In this case, the yellow would be 100 meters for the distance traveled, and for the red, it would be 40 meters. Displacement, on the other hand, is the change in position from start to end, so the displacement is 40 meters for the red, and it's also 40 meters for the yellow. Displacement also should include the direction. So in this case, we would say either positive 40 meters for the displacement for both of these, or 40 meters to the right, depending on how you want to talk about that. When we talk about speed and velocity, there's a difference between not including the direction. There's also can be a quantitative difference between those two magnitudes. For the average speed, what we'll talk about is the distance traveled per time interval. That means that if we're talking about, say, 100 meters covered in, 50 seconds or so, here we would have 100 meters distance traveled divided by 50 seconds would be 2 meters per second. If we had the same time for the path traveled being 40 meters, you would do 40 meters divided by 50 seconds to get 0.8 meters per second. The average velocity, on the other hand, we only look at the displacement. So in this case, 70 meters, 30 meters, 100 meters total over 50 seconds, it doesn't matter that you traveled 100 meters. The displacement is only 40 meters to the right, and so the average velocity is 0.8 meters per second to the right. We only think about the displacement from start to end when we're calculating the average velocity. Another way of thinking about this is that with the displacement, you have positive displacement that is added to negative displacement, so that you don't add positive 70 plus positive 30, you add positive 70 plus negative 30, so that your total displacement is only 40 meters. So the key piece here to understand is that displacement and velocity are vectors. They include a direction, and we use a sign to indicate the direction. So positive 40 meters for the displacement. Here's an example that will help us to distinguish between these, or check to make sure that you are distinguishing between them correctly. So we've got a sprinter, and the sprinter is going to run 100 meters along the track as shown above. Whew, there she goes. So questions. What is her distance traveled? What is her displacement? What is her average speed? And what is her average velocity? So pause for a moment and try to answer those questions. Pause the video, and I'll wait here for you to go over those answers. Okay, so the distance traveled, because she's traveled 100 meters along the track, will be 100 meters. The displacement will be 100 meters to the right, or positive 100 meters. The average speed, we take the distance traveled and divide by the time interval. So we have 10 meters per second. And her average velocity would be the displacement divided by the time, or 10 meters per second to the right, or positive 10 meters per second. Not so hard. Consider the next situation. So now we have the sprinter running 100 meters along the track in 10 seconds, and then slowly walking back over 40 seconds. Now, considering that whole 50-second time, what was her distance traveled, displacement, and average speed, along with her total average velocity? And finally, what's her average velocity for the walk back? So pause the video again, try to answer those questions, and we'll go over them in a moment. Okay, welcome back. The distance traveled here, because she goes 100 meters along the track to the right and then walks back 100 meters, the distance traveled will be 200 meters. Her displacement, on the other hand, because she walks 100 to the right and 100 back, ending up at the same place that she began, will be 0. The average speed, covering 200 meters of distance in 10 plus 40 is 50 seconds, will be an average of 2 meters per second. On the other hand, the total average velocity will be 0 for the displacement divided by 50 is 0. The average velocity for the walk back, though, we can calculate that there was 100 meters in 40 seconds, or 2.5 meters per second to the left, or alternatively, we could call it negative 2.5 meters per second. So that's only for the walk back. How'd you do? Good? When we think about velocity, sometimes we think about velocity as changing. And so in the situation like the runner running along the track, it doesn't make sense to talk about the velocity being 2 meters per second and then 2.5 meters per second over a different interval. We really want to think about what about at this particular moment. When we want to talk about how fast somebody is moving at a particular moment, we're looking at the instantaneous velocity, which describes the motion at one moment in time. In the limit of a very small elapsed time, the average velocity will be the same as the instantaneous velocity. So what this expression indicates is that we could think about our delta t, the time interval, becoming very, very, very short so that it's just happening in an instant. We only cover a very small distance, and so the average velocity over that very, very small interval will be the same as the instantaneous velocity. Let's see if we can make some distinctions by talking about this graph of velocity versus time for half an hour of travel in a car. So the questions are, what is the instantaneous velocity at 0.1 hours? So I look over at 0.1 hours, and up here, our instantaneous velocity is 50, and the units are kilometers per hour. There's no direction given here, so we'll call it positive 50, and we'll think about it as to the right. That's the way I'm thinking about it anyway. The instantaneous velocity at 0.4 hours, we read off 20 kilometers per hour. The average velocity for the whole trip, well, fortunately, a line has been added in here for us, and we see that the average velocity is 30 kilometers per hour. Here's an interesting question. Is the instantaneous velocity ever equal to the average velocity? So we follow this line across, and we see that right here, maybe about, 4 minutes in. 0.1 hours would be 6 minutes. So this is maybe 2 minutes in. So we have 2 minutes in, the average velocity and the instantaneous velocity are the same. And again, over here at 0.2 hours or 12 minutes. And so there's the difference. The graph shows us that the velocity is changing at several places. And so the average velocity is not the same as the instantaneous velocity. Now let's take a look at some motion problems. You'll learn a lot about physics-type problems and how we approach them. So these are a few fairly simple examples. So what is a runner's average velocity if her initial position is 150 meters away from the origin, and she will move to negative 50 meters away from the origin in 25 seconds? I'll go through this one, and you can do the next one on your own. To start with, we'll use our expression for average velocity. The average velocity is the change in position over the change in time, or the final position, s minus s0, over delta t. Now we can substitute in some values, the final position being negative 50, the initial position being 150, and the time interval being 25 seconds. It's a simple step of math to do minus 8 meters per second. This is written as meters inverse seconds, just to be very clear. Here's another one that you can try. How far does a cyclist travel in 1 hour if he is traveling at 20 meters per second? Go ahead and pause and take a go at this, and then I'll join you again and show you the answer. Okay, welcome back. Again, we'll start with our average velocity expression, but this time we'll rearrange it a little bit, multiplying both sides by delta t. So that we have the change in position, or the displacement, is equal to the average velocity times the time interval. We've just multiplied both sides by delta t. And now we'll take the velocity, 20 meters per second, and multiply it by 1 hour. But here we're also going to do a little unit conversion. 1 hour times 20 meters per second isn't going to really give us an answer that we can work with. So instead what we'll do is we'll multiply by 60 for the number of minutes in an hour and 60 for the number of seconds in a minute. And when we multiply all that out, we get 72,000 meters, or better stated as 72 kilometers. Another thing that comes with changing velocity is talking about the acceleration of an object. So when an object's velocity is changing, it's said to be accelerating. And similar to the velocity description, we describe the average acceleration as the change in velocity over the time interval. So we have an expression that's very, very similar to velocity. A is equal to the change in velocity over the change in time, or the final velocity minus the initial velocity divided by the time interval. On the right here, we have an example of a car that is accelerating. It starts out at rest, and we can see here the red velocity vector becomes larger and larger as it moves faster and faster. If we apply some numbers to this, for example, we can apply an acceleration of 15 kilometers per hour per second, then we can actually put some numbers to this. So each second, we know that the velocity is increasing by 15 kilometers per hour. So if we start at time 0 at 0 kilometers per hour, then after 1 second, the car will be traveling at 15 kilometers per hour. After 2 seconds, it'll be traveling 30, and after 3, yep, you're right, it's 45 kilometers per hour. So the car's motion, you'll notice, gets a little bit bigger in each time interval. That's because the velocity is increasing with each second. You'll also notice that the velocity vector is increasing, and that's because there's this constant acceleration. So this motion becomes much more subtle and much more sophisticated than motion at a constant average speed. One thing I like to highlight here is that acceleration does not mean speeding up. Acceleration is a vector showing the change in velocity. So it's possible for an acceleration to describe something slowing down. It's possible, even as we'll see in the future, for an acceleration to show the direction changing. If you turn to the left or turn to the right while maintaining a constant speed, your velocity vector is changing direction, and that's also known as an acceleration. So don't get caught up in the common usage of acceleration to mean specifically increasing your speed. In physics, we use acceleration to describe a change in velocity, whether that's an increase, a decrease in speed, or a change in direction. All right, another example. So let's think about being at a racetrack. So now you're driving your super sports car down the track, still only moving in one dimension. But I want you to try to imagine situations as described below. So go ahead and read, pause, and then we'll come back and talk about some examples of these. Okay, I hope you thought of some interesting ones. Here I'll just give you some specific examples. So for velocity and acceleration both being positive, that means that the velocity should be to the right and the acceleration should be to the right, which means that the velocity will be getting more positive. It means the speed will be getting larger. So this would be traveling along the track while accelerating, while speeding up. If the velocity is positive but the acceleration is negative, that means that the car is moving to the right along the track, but the acceleration is pointing to the left. So the velocity will be getting, the speed will be getting lower. So this would be you slowing down as you move to the right. Velocity acceleration both being negative would involve the car moving to the left and speeding up to the left. Velocity negative and acceleration positive will be sort of the very strange situation where you're moving backwards, but you're slowing down. So that's kind of a strange situation to be in. Velocity is 0 and acceleration positive. If you thought of that exact moment where you're standing still, but you hit the accelerator and you feel the push back in your chair, that's an example of a positive acceleration with 0 velocity. And finally, velocity that's positive and acceleration is 0 would be at a constant speed moving in a straight line along the track, no change in velocity. Here's a few more motion problems, these involving acceleration. Not much different than the velocity ones, just using acceleration to change velocity instead of velocity to change position. What is the average acceleration of a car that changes velocity from 5 meters per second to, whoops, I made a mistake here, 2 meters per second? This should either have 2 meters per second or 2 meters inverse seconds, not both. Anyhow, this change is happening in 10 seconds. We'll use our expression for acceleration. In this case, I'll remove the bar indicating an average, and we'll just call a constant acceleration. Change in velocity over a time interval. V for final velocity, U for initial velocity over time interval. So we have -2 minus 5 over 10, or -7 meters per second squared. The negative indicates that the car is accelerating to the left while the car is moving to the right, so the speed is decreasing, which is what we see here from 5 to -2. Here's another one. Why don't you try it? We have a car traveling at 15 meters per second that has an acceleration of -2.5 meters per second squared. What's that car's velocity after 3 seconds? I'll pause for you. Okay, welcome back. We're going to start with the same equation. Acceleration is the change in velocity over change in time, v minus u over t. But this time we'll rearrange, multiplying both sides by delta t and adding u. So we have final velocity is initial velocity plus acceleration times time interval. Not so hard to change that around. In this case, the initial velocity is 15 meters per second. The acceleration is -2.5 meters per second squared for 3 seconds. So we'll end up at 7.5 meters per second, 7.5 meters inverse seconds. Good? Nice. So that's where we're going for at the start for one-dimensional motion. The essential idea here that we're connecting to is that motion can be described and analyzed by the use of graphs and equations. In this case, we're working with equations. Tomorrow, we'll look at graphs. The terminology that I'm hoping you're familiar with, if you've still got questions, make sure you ask. Position, displacement, distance traveled, velocity, speed, and acceleration. Making sure that you're comfortable using that terminology for the vector terminology, position, velocity, displacement, acceleration, and the scalar quantities, distance traveled, and speed. Keeping those straight can be tricky, and we'll practice that language over the course of the next week. Distinguishing instantaneous and average values, instantaneous values being the ones that change over the course of your motion as you speed up and slow down, the average values being taken over a longer time interval. And finally, we have mathematical definitions for velocity and acceleration, velocity being the rate of change of the position or the change in position over the change in time, and acceleration being the rate of change of velocity or the change in velocity over the change in time. I hope you enjoyed the presentation, and I look forward to seeing you again soon.